Fronts are transition zones between air masses. Mostly they are quite distinct features, with marked changes in temperature, humidity, and the wind occurring on them. We often see cloud and weather signifying their presence, but this is not always the case. Fronts are sometimes poorly defined in weak affairs. When a warm and cold air mass lie next to each other, there is a tendency for the warm air to ride over the top of the cold air due to the differences in density. It is this lifting and cooling of air across a broad area that causes cloud and precipitation to form. Where a front reaches the ground, it is marked on a weather chart. Climatologically, there are three main frontal zones. The first is the polar front, which is the boundary between warm tropical air and cooler polar air. This is the zone along which most mid-latitude depressions form, lying approximately between 35 and 65 degrees north and at around 50 degrees south. Secondly, there is the Arctic front. This is the boundary between cold polar air and the very cold Arctic air, sometimes reaching temperate latitudes in the winter months. And thirdly, the ITCZ, or Intertropical Convergence Zone, which is the confluence between the northeast and southeast trade wind regimes. In addition to the three main fronts, in the northern hemisphere winter, a boundary can also be identified lying over the Mediterranean Sea, approximately east-west. This is called the Mediterranean front. Fronts are called warm or cold, depending on whether warm or cold air is spreading across an area behind the particular frontal boundary. For example, this is a warm front moving from left to right. If the front changes direction for any reason, which on occasion does happen, it becomes a cold front. Let's consider our polar front, which is an almost permanent boundary extending completely around the Earth, separating air masses of a tropical origin from those with a polar source. It is more noticeable in certain areas than others, particularly over the oceans. Normally it is a fairly straight dividing line like this, but occasionally small ripples will develop along it. Mostly, the ripples do not develop any further. They merely run along the front and fade away again. However, if conditions are right within the atmosphere as a whole, the small disturbance will develop into a major middle attitude storm. A polar front depression. Let's look in simple terms at how this happens. As the ripple forms, warm air starts to override cooler air. As soon as this happens, the atmospheric pressure at the surface falls slightly. This falling of the surface pressure begins to induce a rotation. This rotation helps push more of the warm air over the top of the cooler air here, and correspondingly, helps ease a wedge of cooler air underneath the warmer air here. Hence we get to areas along the original polar front, where warm air is overriding cold air. As this overriding becomes more pronounced, the pressure falls still further, with enclosed isopods forming the pattern at the surface. You will see the familiar shape of a frontal depression now in view. The lifting of air along the polar front here and here, due to the density differences, forms the layered cloud, the stratocumulus, stratus, limbostratus and alpastratus type, that we associate with fronts. This portion forms the warm front and this, the cold front. The convergence of air in and around the low-pressure system in general and along the fronts in particular also increases this uplift of air. At this stage we have what is known as a warm sector depression, with a warm front, a cold front and a warm sector. Let's look at these constituent parts in a bit more detail. The warm front. If warm air is replacing cold air, then we call it a warm front. The slope of a typical warm front is 1 in 150. Here's a side view showing the main areas of cloud associated with such a front. This is the sequence of cloud that an observer on the ground would see if the front was approaching. Cirrus stratus, giving us a halo around the sun all moon. Altostratus, making the sun all moon look as if it was behind ground glass. Limbostratus, thick and threatening looking cloud. Stratocumulus, and finally stratus, the lowest of all the clouds. Notice how the main area of precipitation starts on 200 to 300 nautical miles ahead of the surface front as the base of the cloud gradually lowers. The 0-degree isotherm also lifts to a higher level in the warm air behind the front, and notice also the fold or break in the tropopause and the position of the jet stream. In this picture, the jet is coming out of the diagram towards us. We've considered the cloud ahead of a warm front, but what happens to the other elements of the weather? First, let's look at the wind. As the front approaches, the wind will usually start to increase. It will also back or turn anti-clockwise between 10 and 30 degrees. However, on the passage of the front, it will veer or turn clockwise markedly, sometimes by as much as 70 or 80 degrees. Usually by around 30 to 40 degrees. The air mass ahead of a warm front is usually polar maritime or returning polar maritime air, and so the visibility is usually very good well ahead of the warm front. It only really deteriorates as the precipitation starts to fall from the front. The precipitation is usually persistent once it has started and falls mainly as rain or drizzle or a mixture of the two. It is characterized by its steadiness rather than intensity. In winter with low temperatures, snow or rain ice are a possibility ahead of a warm front, which are major aviation hazards. Once the front has passed, we are now in what is called the warm sector, which is usually tropical maritime air. This is a stable air mass, and the characteristics of this part of the polar front depression are its fairly uniform base of extensive stratus or stratocumulus cloud, the relatively poor visibility. The steady wind, often strong but not particularly gusty. The mainly dry conditions, although patchy light drizzle is possible. We shall go summary of all the effects of the passage of a warm front later in the lesson. The speed of movement of a warm front can be estimated using a simple technique. All you need is a weather chart with a geostrophic wind scale on it. Measure the isobaric spacing on the front like this. Use that measurement on the geostrophic wind scale and then multiply the answer by 2/3. This gives the approximate speed to the front in the direction of the isobars behind the front itself. Now let's look at the cold front. The cold front is replacing warm tropical maritime air with cooler polar maritime air. The cold front is almost a warm front in reverse, but note that the average slope is different, usually 1 in 1950. Most of the weather occurs on the cold front and just behind it. This makes its passage quite sudden, with little warning that it's approaching. Notice how the clouds that make up the front are only really seen from the ground once the front is clearing away. The main band of heavy precipitation is between 50 and 100 nautical miles behind the surface feature. Let's look at the main points on our diagram. The sequence of clouds that an observer would see on the ground through the passage of a cold front are: stratus, perhaps hiding some embedded convection in the form of the cumulonimbus cloud. Then we have stratocumulus layers, altostratus, altocumulus, cirrostratus, cirrus. Remember, this is a typical cold front, also called an anacold front, but not all the cloud types will be seen on all occasion. We can have catacold front, which tends to be much less active with fewer cloud layers due to descending air. There are some other interesting things to note on the diagram. The 0-degree isotherm falls in the colder air behind the front. The break or fold in the tropical pores, the jet stream, positioned in the warm air with the direction of the flow going into the screen. In a similar manner to the warm front technique, the speed of movement of the cold front can be estimated. Again, using a weather chart with a geostrophic scale on it, measure the isobaric spacing on the front like this. This gives an approximate answer for the speed of the front in the direction of the isobars behind the front itself.